Good morning, dear students. Our next topic, it is enzyme catalysis. Okay. So this enzyme catalysis, normally we have seen so many chemical reactions, and those chemical reactions which they are carried out in the presence of catalyst, isn't it? They might be some catalyst initiated reactions. See here, enzyme catalysis means, see, in our body, so many organic reactions are taking place, isn't it? In our body as well as in the case of plants also. So many organic reactions are there taking place, and these organic reactions, they are catalyzed by some organic substances called as enzymes. Okay. These organic reactions, they are catalyzed by some organic substances called as enzymes. And also these enzymes, they are complex protein molecules. The enzymes, they are complex protein molecules, and also these protein molecules, they are having a very high molecular mass. Protein molecules are having a very high molecular mass, and also this molecular mass, it will be usually about it will be greater than 10,000. Okay. So that is what is called as enzyme catalysis. So the phenomenon by which the organic reactions or the chemical reactions taking place inside the body of plants and animals, usually they are catalyzed by the presence of certain organic substances called as enzymes. And also these enzymes are complex protein molecules with a very high molecular mass of 10,000. Okay. Then next you have to go through some of the examples of this enzymatic reactions. Okay. So the first example is in the case of soya beans. Okay, in the case of soya beans, this urea, it is converted to carbon dioxide and ammonia. Okay, in soya beans, this urea, it is this soya beans has got an enzyme urease, and due to the presence of this enzyme urea, it is converted to ammonia and carbon dioxide. Okay, so you have to write down the equation. Thus urea, the formula is NH2CONH2. This is urea. In the presence of the enzyme urease in soya beans, this urea will be converted to ammonia plus CO2. Okay, so this is the first example. Then the second example, in yeast, one enzyme is there. Yeast has got zymase as well as invertase. Here I am writing the reaction or the reaction of the enzyme zymase. Okay. So in the zymase enzyme present in yeast, it will be converting the glucose to alcohol as well as carbon dioxide. Okay. So glucose, the formula is C6H12O6. 2 molecules of glucose. So this is glucose. So glucose, in the presence of the enzyme zymase, it is converted to alcohol and water to C2H5OH. C2H5OH is alcohol and, sorry, not water, it is carbon dioxide. Okay. Ethyl alcohol and carbon dioxide. Okay. So this is the action of enzyme present in yeast. Then the third one, in germinated barley seeds. In germinated barley seeds, this diastase enzyme is present. Okay, so this diastase enzyme, it will be converting starch to maltose. See, this is the formula for starch, C6H10O5 N times. So this is starch. So this diastase present in germinated barley, it will be converting this starch to this maltose. Okay, so starch plus N molecules of H2O in the presence of the enzyme diastase, giving it will be converted to maltose C12H22O11. Okay. Then again, one more reaction is there. The reaction of the enzyme catalysis of maltase. Okay, maltase is another enzyme. So again, C12H22O11, fourth one, C12H22O11, that is maltose. Okay, this is maltose. This also maltose. So this maltose, it will be on hydrolysis in presence of the enzyme maltase. This will be converted to C6H12O6 plus C6H12O6. What is the purpose of writing these two molecules? See, the molecular formula is the same, but the structural formula is different for glucose as well as fructose. So the one is glucose and the another one is fructose. Okay. So these are some of the enzymatic reactions. So here you have to go through some of the examples. The enzyme present in yeast, then urease, then in germinated barley seeds diastase, and also the reactions. Okay, then one more reaction is there with the reaction of the enzyme invertase. Okay, so this invertase, it will be converting cane sugar to glucose and fructose. Okay, sorry, there is a mistake. See here, this maltose, in presence of maltase, it will be converting to glucose. Okay, to C6H12O6, 2 molecules of glucose. The enzyme invertase, invertase is converting this cane sugar to glucose and fructose. Okay, cane sugar, that is C12H22O11, C12H22O11 plus H2O. In the presence of the enzyme invertase, it will be converting to glucose and fructose, C6H12O6 plus C6H12O6. This is glucose and this is fructose. Okay. So this is cane sugar. So cane sugar on hydrolysis in the presence of the enzyme invertase, it will be converting glucose to, glucose and fructose. Then you have to go through some of the special features of this enzymes. Okay. So the first one, usually these enzymes are specific in their reaction. First point, enzymes are specific in their reaction. Enzymes are specific in their reaction. See, usually the specific means the reactions, the enzyme used in one reaction cannot be used in another one. That means it should be one of the enzyme, it will be reacting with that particular substrate molecule itself. Okay, and also the shape of the enzyme is such that, see here, I'll show you the diagram in the text. See here, the shape of the enzyme is such that it will be perfectly fitting into the substrate molecule. The enzyme will be perfectly fitting into the substrate molecule. Okay, so that an enzyme substrate complex is formed, and again the products will be formed. Okay, so here the shape of the molecule, shape of the enzyme will perfectly fitting into the substrate molecule at the active site. So this is the active site of the substrate molecule, and this into this active site, the enzyme molecule, it will be perfectly fitting. See here, it will be perfectly fit in the enzyme substrate complex, and then the reaction proceeds to form the products. Okay, so that is what is called as the specificity of the reaction. So the enzymes are specific, that means it fits the active site. So the first point is that it fits the active site. Then it comes in close contact with proper orientation. Comes in close contact with proper orientation. Comes in close contact with proper orientation. Proper orientation, and then afterwards what happens? The reaction takes place. Okay, so that is the specificity of the enzyme. Then the second one is that these enzymes are sensitive to temperature. The enzymes are sensitive to temperature. That means usually these enzymes, it will be acting effectively at a temperature of 298 Kelvin to 310 Kelvin. That is the most efficient temperature of this enzyme, that is between 298 and 310 Kelvin. And also the temperature at which the reaction rate is maximum. The temperature at which the reaction rate is maximum, it is called as the optimum temperature. Okay, the temperature at which the reaction rate is maximum, it is called as the optimum temperature. And usually the optimum temperature in human body, it is about 37 degrees Celsius. That means the enzymes will be acting most effectively at this particular temperature. So what happens is that, see, while we are having fever, what happens? The body temperature increases, isn't it? So while this body temperature increases, the enzymes will stop acting. That is, the enzymatic action will not function above this particular temperature. Okay. Above this 37 degrees Celsius. So that is why very high body temperature is quite dangerous for human beings. Okay. So the optimum temperature for the enzymatic action is 37 degree. Above that, what happens? The enzymatic reactions will stop. So if the enzymatic reactions are stopping, what happens? The physiological reactions going on inside our body will also be stopped above this particular temperature. So normally that is why while we are having high fever, doctors are prescribing us to low down this temperature. Okay. Then the third one, that is the enzymatic action. It will be varying with pH. Enzymatic action, it varies with pH. Okay. So usually the rate of a reaction, it will be the rate of the reaction, it is maximum at a particular pH. Okay. The rate of the reaction, it will be maximum at a particular pH value. And normally for human beings, the optimum pH, that means that that particular pH, we can call it as the optimum pH. That is, the rate of the reaction is maximum. And this optimum pH or the enzymatic action will be maximum at a pH of 7.4. Normally, see, our blood has got a pH of 7.4. So at this pH, the enzymatic action will be best functioning. Okay, best occurring. So that is the third point. Then the fourth point is that the catalytic activity is usually, as in other reactions, the catalytic activity is usually inhibited or poisoned. The term, it is poisoning, isn't it? The catalytic activity is usually inhibited or poisoned by the presence of certain other chemical substances. Normally, if our body has got, if some other metals, etc., if get inside our body, what happens? It will be complexing with the enzymes. Okay. So normally this Ag plus, Hg2 plus, etc., are metals which are poisonous to our body, or which are harmful, very harmful to our body, isn't it? So if the presence of such metals are there, it will be inhibiting the action of enzymes. Okay. So enzyme, normally it will be having a functional group SH. Okay. So this enzyme, this is enzyme, and it has got a functional group SH. So if it is reacting with this Hg2 plus, what happens? This the two protons, it will be replaced by this Hg2 plus. So this is the enzyme with the functional group SH. So if Hg2 plus get inside our body, what happens? This Hg2 plus will be having a bond with this enzyme. Okay. So this two protons will be replaced by Hg2 plus. So it will be like this, S, then again S, then Hg. Okay. See how a bond is formed. So this will be acting as a poisoning, or it will be inhibiting the activity of enzymes. So this is the reaction with Hg2 plus. Similarly, we can write the reaction with Ag plus also. So enzyme with functional group SH plus Ag plus. So here what happens? In both cases, poisoning is there, isn't it? Here also poisoning. In both cases, poisoning is there. So what happens? This enzyme, then S, Ag. Okay, a bond is formed between the enzyme plus H plus. Here it has got 2H plus. Okay. So this is the catalytic inhibition or the poisoning of the enzymes. Okay. Then some of the drugs, usually it will be affecting the enzymatic action, or it will be preventing the bacterial action by making the enzymes properly functioning. Okay, so some drugs are there, that is, some examples are there in your textbook, that is, for example, sulfur drugs, then penicillin, sulfur drugs, then penicillin, then streptomycin, sulfur drugs, penicillin, streptomycin, these all prevents the bacterial action. Okay, usually these are some drugs which are given for certain diseases. So these drugs will be preventing the bacterial action, and it prevents us from pneumonia, pneumonia, then dysentery, then cholera. Okay, so these are the drugs which are effective in treating this pneumonia, dysentery as well as cholera. Then the next one, that is we have to what are activators or coenzymes. So the next point, that is the activators or coenzymes. So activators, the word itself means it will be activating the action of enzymes. Okay, activators, or we can say that the coenzyme. So some enzyme, some metal ions, it will be promoting the activity of the enzymes. Okay, so one of these coenzyme or the activators, they are metal ions like Mn2 plus, then Cu2 plus, etc., which will be promoting the catalytic action. And also NaCl also sometimes enhances the catalytic action. So Na plus, it will be enhancing the catalytic action of the enzyme amylase. Okay, so these enzymes are specific, and here sodium chloride or Na plus will be enhancing the catalytic activity of amylase. So it can be called as a coenzyme. Okay, then the next one, that is very important, that is the Michael-Menten mechanism. Okay, Michael, A-E-L-I-S, Michael-Menten, M-E-N-T-E-N, Michael-Menten mechanism. That is the mechanism of enzyme catalyzed reaction. This is very, very, very important. It is a university question which is usually asked. Okay, so normally for an enzyme reaction, what happens is that this enzyme, it will be reacting with a substrate molecule. So enzyme, we can denote it by the letter E, and the substrate molecule by S. Okay, so when this enzyme and substrate are reacting, what happens is that an enzyme substrate complex is formed. Okay, so enzyme reacts with substrate molecule. This is enzyme, then this is substrate molecule. So while this reaction is going on, an enzyme substrate complex is formed. So we can write here the forward reaction as the rate constant as K1, and the backward reaction, the rate constant as K inverse. Okay, so this is the enzyme substrate complex. Enzyme substrate complex. So again, this enzyme substrate complex, it will be decomposed to give the products. One of them products plus the enzyme, we will be obtaining back. Okay, so the rate of that particular reaction, let it be K2. Okay, so this is the reaction, enzyme reaction with substrate giving enzyme substrate complex. Again, it is decomposes to give the products. Okay, so here we can say that the overall reaction of the enzyme, it is the total enzyme, it is converted to the enzyme substrate complex, and later on it is regenerated to form the to get back the enzyme, isn't it? So here we can apply one of the steady state approximation. Okay, have you heard of steady state approximation? Steady state approximation means the rate of the concentration of ES, that is the enzyme substrate complex concentration, it is a constant. Okay, or with respect to time, the rate of disintegration of this ES will be equal to 0, that is dES by dt, it will be equal to 0, that is by applying, this is the steady state approximation, by applying steady state approximation. Steady state approximation means the rate of formation of this or the concentration of this ES, enzyme substrate complex, it will be equal to a constant, or while differentiating with respect to time or with respect to t, this d by dt of ES will be equal to 0. So this is the steady state approximation. So here we have to apply this particular rule, and also one more equation is there, the formation. So the rate of formation of this ES will be equal to a constant, isn't it? So we can write the formation of this enzyme substrate complex and also the decomposition of enzyme substrate complex. Okay, so the first step is formation of enzyme substrate complex. So here some mistakes are there in your textbook. You have to correct it, okay? Or else you have to go through this derivation and then you have to correct it in your textbook. So the formation of ES will be equal to, see in this equation, what are the reactions leading to the formation of ES? See, rate of formation of ES is equal to K1 into concentration of E into concentration of S. Okay. So the formation of ES will be equal to K1. That is the forward reaction. K1 into concentration of E into concentration of S. Okay. Then the next step, the breakdown or the decomposition of ES. Decomposition of ES. So, see here, the decomposition of ES means this reaction, isn't it? That is K inverse into, here this ES is decomposed, isn't it? So, K inverse into ES, that is K inverse into ES. So, in this step, this ES is disintegrating to form the products. Plus, then again, the next step is K2 into ES. Okay. Plus K2 into ES. So that is the rate of decomposition. Okay. K1 into ES plus K2 into ES. So here, see the formation of ES is equal to K1 into, that is this particular reaction. Here ES is formed. Then in two steps this ES is disintegrated, that is K inverse into ES, and again here at this stage also this ES is disintegrated to form products and enzymes. So K2 plus K2 into ES. Then you have to apply the steady state approximation, that is the concentration of ES will be a constant, or d by dt of ES is equal to 0. So we have to equate this equation to 0. Okay. So both of this will be equal, that is K1 into E into S. K1 into E into S, that is formation of ES. Then formation of ES is equal to breakdown of ES, that is equal to K inverse into ES plus K2 into ES. Okay, formation of ES is equal to breakdown of ES. Then again you have to simplify this equation, that is K1 into E into S minus, take to the left side, minus K inverse into ES minus K2 into ES, that is equal to 0. Okay. So this is equation number, say one more equation is there, the rate of formation of products, that is equal to, normally by applying the kinetics of this particular reaction, the rate of the reaction R is equal to, what is it, minus ds by dt, that is the disintegration of the substrate, or it will be equal to what, dp by dt, the rate of formation of products, isn't it? So here the products formation, what is the reaction rate constant, K2, isn't it? That is equal to, we can say that it will be equal to K2 into ES. So rate is equal to K2 into ES. That is one equation. Okay, that is the first equation. Okay, you have to write it at the first step, as the first step. Okay, rate is equal to K2 into ES. That is equation number 1. So here you have to put this as equation number 2. So this equation number 2. I will write the two equations once again. That means the rate is equal to K2 into ES. That is the first equation. And the second equation is K1 into E into S minus K inverse into ES. K inverse into ES minus K2 into ES minus K2 into ES is equal to 0. Okay. So this is the second equation. Then see, now we have to write some substitutions. See, let E0 be the initial concentration of the enzyme. Okay. E0 be the initial concentration of the enzyme. E0 be the initial concentration of the enzyme, and also at any time we can write this equation, E0 will be equal to the concentration of E0, let it be equal to concentration of E plus concentration of ES. Okay, that means At any time we can write it as it will be equal to the sum of the concentration of E and ES. Okay, ES means it will be converted to the enzyme substrate complex and also the enzyme alone. Okay, so that will give the initial concentration of the enzyme. So from this equation we can write the concentration of E, isn't it? So concentration of E is equal to concentration of E0 minus concentration of ES. Okay, concentration of E0 minus concentration of ES. Let it be equation number 3. Okay, then substitute this equation, the value of the value of E in equation 2. Okay, substitute equation 3 in equation 2. That is, you have to substitute for E. Okay, so how will you substitute? That is K1 into what is E? E is equal to E0, concentration of E0 minus concentration of ES into, again one S is there, isn't it? Into concentration of S minus, this is the equation, minus K inverse into ES minus K2 into ES, that is equal to 0. Okay, K1 into this much. Okay, we have to substitute. So this is a common bracket. Okay, K1 into E0 minus ES into S minus K inverse into ES minus K2 into ES is equal to 0. So again you have to simplify this equation. That is K1 into E0 minus K1 into ES into S. You have to open the brackets and multiply. Okay, K1 into E0 into S minus K1 into ES into S minus K inverse into ES minus K2 into ES minus K2 into ES, that is equal to 0. Okay, so then from this equation you have to write down what is K1 into E0 into S. That is K1 into E0 into S. K1 into E0 into concentration of S, that is equal to K1, this will be going to the right side, K1 into ES into S plus, this will be going to the right side, so it will become plus K inverse into ES, then again this will be going to the right side, plus K2 into ES. Okay, so these are the this is the next step. So K1 into, we will be having K1 into E0 into X. Yes, so again see here, what is the common term here? ES, isn't it? ES is the common term, so you have to take this ES outside and also write the equation for ES. Okay, so then ES will be equal to, what is ES? K1 into E0 into S, K1 into E0 into S divided by, then again here it will be K1 into S plus K inverse, here ES is taken outside, isn't it, plus K2. Okay, ES is taken outside, so that K1 into E0 into S divided by K1 into S plus K inverse in K inverse plus K2 into K2. Okay, so this you can write it as a bracket here. Okay, so then we had got the value for ES. Then you have to substitute this equation. This is equation number 4. Substitute equation 4 in equation 1. Okay, what is equation 1? Equation 1 is rate is equal to K2 into ES. Okay, so equation 1 is rate is equal to K2 into ES. Then you have to substitute for ES. That is equal to K2 into, then what is ES? ES is K1 into E0 into S divided by K1 into S plus K inverse plus K2. Okay, so this is the substitution. Okay, then in the next step you have to divide this numerator and denominator by K1. Okay, so next step, divide numerator and denominator by K1. Divide numerator and denominator by K1. So while dividing the numerator by K1, this K1 got cancelled, isn't it? So it will be equal to K2 into E0 into S. So rate is equal to K2 into E0 into S. That is after dividing by K1 numerator. Okay, then next you have to divide the denominator by K1. Okay, so here K1 is divided by K1. So S, okay, plus K inverse plus K2 divided by K1. So here it becomes S plus in the second term there is no K1. So it will be like this, K inverse plus K2 divided by K1. Okay, so that is the next step. So here these three are constants. K inverse is a constant, K2 is a constant, K1 is a constant. So we can substitute it by another constant Km. So therefore rate R is equal to K2 into E0 into S, E0 into S divided by concentration of S plus Km. Okay, so here Km is called as the Michael-Menten constant. Michael-Menten constant. Km is called as the Michael-Menten constant, and Km is equal to, Km is equal to K inverse plus K2 divided by K1. Okay, so Km is called as the Michael-Menten constant. So this is the equation for this enzyme catalysis. That is, rate is equal, this is a very important equation, rate is equal to K2 into E0 into S divided by S plus K. Okay. Then you have to go through some of the conditions of this reaction. Okay. So 4 conditions are there, and the first condition is that at high concentration, at very high concentration, what happens is that the initial concentration of E0, it will be equal to the enzyme substrate complex. That means at very high concentration, there will not be any free E, isn't it? The enzymes will not be free. That means in all the enzymes, it will be converted to ES. So we can say that at very high concentration, ES will be equal to E0. Okay. All the initial enzyme will be converted to an enzyme substrate complex. So what is our first equation? Rate is equal to, so the first equation is rate is equal to K2 into ES, isn't it? Our first equation is rate is equal to K2 into ES. That is our first equation. So substituting this value in the first equation. So rate will be equal to K2 into, instead of ES, we can write it as E0. Okay. Rate is equal to K2 into E0. So this rate will be equal to, in this enzymology, it will be represented by Vmax, or we can write the equation as Vmax is equal to, rate is equal to, Vmax is equal to K2 into E0. That is one condition. Okay. Then again, again we have got the equation, the Michael-Menten equation is rate is equal to K2 into E0 into S divided by S plus K, isn't it? So I am writing the equation, that is rate is equal to K2 into E0 into S, rate is equal to K2 into E0 into S divided by S plus K, isn't it? So that is the equation we obtained as a Michael-Menten equation. So again you have to substitute for this equation. See, Vmax is equal to K2 into E0. So we can substitute for K2 into E0 in this equation. So rate is equal to K2 into E0 is Vmax. K2 R is equal to Vmax into concentration of S divided by S plus K. Okay, you have to rearrange this equation. So from this equation, rate is equal to Vmax into S divided by S plus K. So that is the first condition. At high concentration, the rate will be equal to this much. Then the second condition, then the second condition, that is when Km is very much greater than this concentration of the substrate. Okay. When Km is very much greater than the concentration of the substrate. So we have got the equation as R is equal to K2 into concentration of E0 into concentration of S divided by S plus K. This is the Michael-Menten equation, and it is very important. You have to study the equation by heart. Okay. So when Km is very much greater than the concentration of S, we can say that this S can be neglected. Okay. S can be neglected. S can be neglected. So we can rewrite this equation as R is equal to, S we can avoid. So R is equal to K2 into concentration of E0 divided by S can be neglected again. So that will be equal to Km. Okay. So K2 into E0 divided by Km. So again, what is K2 into E0? Sorry, here S we cannot neglect here. Only this S value can be neglected since it is an addition term. But here it cannot be neglected since it is a multiplication term. Okay. So this K2 into E0 into S. K2 into E0 into S divided by Km. What is K2 into E0? K2 into E0 is Vmax. Vmax into concentration of S divided by Km. Okay. Then again, Vmax by Km, we can say that they are all constant. So we can put it by another constant K dash into S. Okay. So the rate is equal to K dash into S. That means the reaction, it will be of first order. Okay. See, the rate is depending on only concentration of the one of the reactant, isn't it? So we can say that the reaction is of first order when Km is very much greater than S. Okay, that is the second condition. Then the third condition is that when the substrate concentration is very much greater than Km. Okay, when the substrate concentration is very much greater than Km. So the equation is R is equal to Vmax into concentration of S divided by concentration of S plus Km. That is the Michael-Menten equation by substituting with Vmax. And if S is very much greater than Km, we can neglect the term K, isn't it? It is an addition term. No more, so much changes will not be, not very high changes will not be occurring to the denominator by the addition of a small quantity like Km, isn't it? So we can neglect the Km. Okay, neglect the constant Km. So we can rewrite the equation R is equal to Vmax into S divided by concentration of S. Both this got cancelled. So that will be equal to Vmax. Okay. So Vmax means it is again a constant. Vmax is a constant. That means we can say that the reaction, it will be equal to a constant, isn't it? That means the reaction is of a zero order. It does not depend on any one of the concentration of the reactant, isn't it? So the reaction is a zero order reaction. And then one more condition is there. That is the fourth condition. That is when Km is equal to the substrate concentration. Okay. So we have to write the equation again. R is equal to Vmax into S divided by S plus Km. Vmax into S divided by S plus Km. So again we have to substitute for Km, isn't it? So Km is equal to S. So that is equal to Vmax into S divided by S plus Km. So instead of Km we can put it as S. So S plus S, that will be equal to 2S, isn't it? So Vmax into S divided by 2S, that is S got cancelled. So R is equal to half into Vmax, isn't it? R is equal to half into Vmax. So that is another condition. So these are the four conditions with the help of we are deriving from the Michael-Menten equation, and you have to go through all these conditions also. And then one more definition is there, K2. So here in the first step we had seen one equation, that is rate is equal to K2, isn't it? Rate is equal to K2 into concentration of ES, isn't it? So what is K2 here? K2 is called as the turnover number of that particular reaction. Okay, you have to go through that definition also. This turnover number, it is also very important. So in this reaction, this K2, it is called as the turnover number of the reaction. So here this turnover number means it is the number of molecules converted in unit time by one molecule of enzyme. by 1 molecule of enzyme. That is what is called as the turnover number. It is the number of molecules converted in unit time by 1 molecule of the enzyme. Usually the K2 value, it will be ranging from, it is a number, it will be ranging from 100 to 1000 per second. Okay, that is the general value, and sometimes it will be going as high as 10 raised to 5, 10 raised to 6 per second. In that range also this turnover number will be going. Okay, so K2, it is called as the turnover number, and it is the number of molecules converted in unit time by 1 molecule of the enzyme. Okay, so that is called as the turnover number. Okay, so this much is our portions, that is catalysis is also over. So you have to go through all these, and in our next session we will be having the discussions from each portions. Okay, thank you.